Dear students, I welcome you for the today's lecture related to the heat exchanger designing. Now, one by one, we will study the. There are two different types by which the heat exchanger designing is done. One is the log mean temperature difference, in which we are knowing the mass flow rates for the hot fluid and cold fluid and the temperatures related to that. The second method is that the heat exchanger that is already available with us, and for that purpose we are predicting the outlet temperature for the hot and cold fluid streams. That is the effectiveness method or NTU method. Initially we will talk related to this log mean temperature difference method, in which we are having the mass flow rates and the temperatures, and for that purpose we are designing the details of the exchanger layout. The designing steps for the heat exchanger are: the first, you have to calculate the heat load Q, in which mass flow rate for the hot fluid, cold fluid, that is incorporated. The temperature for the inlet temperature and the outlet temperatures for the hot and cold fluid should be known. Then the physical properties, that is viscosity, density, specific heat and thermal properties, are to be collected at the mean temperature of the hot fluid and cold fluid. Then you have to define the exchanger type, in which whether it's a shell and tube heat exchanger or a plate type heat exchanger or a spiral type heat exchanger. However, the designing procedure is more or less same. Then assume the suitable value of U from the literature. Then calculate the log mean temperature difference delta Tm. Then after calculation of this U, that is the overall heat transfer coefficient, and delta Tm, you will be able to calculate the area required. Then you have to define the exchanger layout. While defining the exchanger layout, you have to calculate select the dimensions of the tube, that is thickness, diameter, length of a tube. Then decide the pitch arrangement, that is whether it's a triangular pitch arrangement, square pitch arrangement, or a rotated square pitch arrangement. Then decide the number of passes of the tube side as well as shell side. Then calculate the outside surface area for one tube. From there, the number of tubes that can be calculated. Then after the calculation of number of tubes, you will be able to calculate the bundle diameter. Then after the calculation of bundle diameter, you will be able to calculate the shell diameter, and after the calculation of shell diameter, you will be able to calculate the baffle spacing. So this is incorporated in the exchanger layout. Then you have to calculate the individual heat transfer coefficients, that is the HI, the inside heat transfer coefficient and the outside heat transfer coefficient. For that purpose, you have to calculate the area, velocity, diameter or equivalent diameter, then Reynolds number, Prandtl number, and use the certain specific correlations. This is to be calculated for the fluid which is flowing inside the tube and the fluid which is outside the tube. Then next is calculate the overall heat transfer coefficient. Compare the value of the assumed value with his overall calculated value. If they match, then proceed for the next step of calculation of log delta P calculations, pressure drop calculations. If the pressure drop calculations are within the limits, then proceed for the next step of optimization of the designing. So one by one you have to go step by step for designing purpose. The next, individually we will go into the details of every point now. So designing the steps for heat exchanger, first is to define the duty or the load, that is the heat transfer, amount of the heat transfer that is to be taken in a heat exchanger. And for that purpose, we are having the basic formula of Q, which is equal to mCp delta T. This is should be applicable for hot fluid as well as for the cold fluid. So I will be able to calculate the Q values for the hot fluid and the Q values for the cold fluid. If considering there is no heat losses, that means the amount of the heat given by the hot fluid will be same as the amount of the heat that will be absorbed by the cold fluid. So on one side there is a hot fluid and on the another side there is a cold fluid. The fluid which is on the tube side that will flow through these tubes and will come to the another end and will go out from the another end. So this is the amount mCpC, mass flow rate of the cold fluid, heat capacity of the cold fluid, and temperature difference for the cold fluid. That is, if CpCi and TCO, this will give you the delta T's. And in case of a condensation or boiling processes, Q, which is equal to the m lambda, that is the latent heat. In addition to the sensible heat, I have to add the latent heat also whenever there is a phase change. And the third formula required, that is U, which is equal to UA delta Tm. So basically in heat transfer or designing of the exchanger, the Q heat load, you require to consider the three formulas, that is mCp delta T, UA delta T, and the m lambda. The next is second point, that is related to the physical properties. Collect all physical properties for the cold fluid and the hot fluid and the material of construction. That means your tube site thermal conductivity that is needed. The different physical properties when you talk, it incorporates the density, specific heat, heat capacity, thermal conductivity, viscosity are needed. And the thermal conductivity of a material of a construction, that is also needed. These fluid properties are to be evaluated at a mean stream temperature, that means the average temperature of the individual stream. हॉट फ्लूइड का एवरेज जो कुछ रहेगा उसके मीन टेम्परेचर पे density, viscosity, thermal conductivity and specific heat are to be defined. Then water is a very common fluid that is used in our chemical engineering processes for cooling purpose, and one should know the physical properties for the water, and that is generally the viscosity for water, that is 0.07 Newton second per meter square to 0.01 Newton second per meter square. The density of water is the 1000 kgs per meter cube. Then Cp is 4200 joules per kg degree Celsius, and the thermal conductivity for water is 0.614 to 0.66 watt per meter Kelvin. So this physical properties one should know it. Then the density for the steam or for the air, that means the vapor phase, that is 1.17 kgs per meter cube. In case of a heating purpose, steam that is mostly used for heating purpose. Then thermal conductivity of metal, that is required. The next is decide the type of a exchanger, that is based on the construction, whether it's a shell and tube, plate type, evaporator, or reboiler, whatever the type of a exchanger it is, then you have to select it. This is a general procedure in which I am going to discuss related to the shell and tube heat exchanger specifically. But with minor modifications, say for example, the calculation of velocity, calculation of the area, they may vary depending on the type of a exchanger. For a plate type exchanger, the area calculations will vary. Then select the different trial values for the overall coefficient. And heat exchanger is typically involves the two fluids separated by a metal wall. So the overall heat transfer coefficient values that is considered for from the literature, that is water to water, the overall heat transfer coefficient values, they are considered from 850 to 1700. Then for the water to oil, that is 100 to 350 watts per meter square Kelvin. Water, this is for water to oil, that is 100 to 350. Water to gasoline or kerosene, that is 300 to 1000. Feed water heater. Then steam to light fuel oil, that is 200 to 400. Then steam condensation 1000 to 6000. Then gas to gas, that is 10 to 40. Then water to air, that is 30 to 60. Now, in general, looking at this, you should be able to remember this. Water to water, that is 850 to 1500. Then all these are your kerosene, oil, they are your organic solvents. OS, that is organic solvents. So in case of organic solvents, it is 100 to 350 is the general value. And in case of gases, it is 100 to 40. That means the lower values of heat transfer coefficient are there for the gases. Above that, for organic solvents, which is from 100 to 350, above that there is a water, and finally it's a steam. So first lowest values are for the gases, then for the organic solvent, then for water, and then for condensing steam. So condensing steam, if it's a new metal, then its value can be more than 10,000 also. So you can remember these values. However, when there is a gas and the organic solvent, so values will range from 100 to 300, 10 to 300 for gas to organic solvents. The values will be from 10 to 300. So all this is related to the assumption. From these values of literature, these are representative values of the overall heat transfer coefficient in the heat exchanger. So one can consider these values and can proceed for the next step of calculations. Next is to calculate the log mean temperature difference. And this mean temperature difference, that is the delta Tm, which is equal to the Ft into delta TLM. Ft will be used whenever there is more than one pass on either of the sides. Either can be on the tube side or can be on the shell side, or else delta Tm, which is equal to delta TLM. So Ft will be equal to the 1 in that cases. So log mean temperature difference is the temperature delta T1 from one end minus delta T2 from the another end upon ln of delta T1 upon delta T2. The next is calculate the area of heat exchanger. We have assumed the value of the U. We have calculated the delta Tm, and in the first step we have calculated the value of Q. So the remaining is the area calculations. So at this point we'll calculate the area required for the heat exchanger, which will be suitable for this load, and with this temperature difference, log mean temperature difference, and for this overall heat transfer coefficient. Then after the calculation of the area, there is a defining a exchanger layout. So as this area is there, how I am going to define the exchanger layout, that will directly correspond to my area calculations. Defining the exchanger layout, that will correspond to the area calculations. So exchanger layout, this is also called the tube sheet layout also. Now in this, first the tube dimensions that is to be defined. Whenever the tube dimensions they are, it is the what should be the diameter of a tube, what should be the thickness of the tube, what should be the length of a tube. In general case, the diameter of the tubes used is 16 millimeter to 50 millimeter. That is the average diameter that will is preferred. In case of a heat exchanger, the 19 millimeter diameter tube, they are more commonly used. 19 millimeter diameter tubes, they are more commonly used. And in case of evaporators, the diameter of the tube that may go up to the 50 millimeters. 50 millimeters. Then what should be the thickness? Thickness is depending on the pressure. Pressure, that is our formula of PD upon 2Fj, that is used. The standard formula for calculation of the thickness for inside for the pipe. Then what should be the length? Length, there are standard tube lengths available, that is a 6 feet, 8 feet, 12 feet, 16 feet tubes, they are available in the market, and depending on the availability in the market, one has to decide this length of the tube. Not only that, but the area which is available in the process plant में available रहने वाला area, that also decides this length. कितना लंबा चाहिए हीट एक्सचेंजर या कितना डायमीटर में बड़ा चाहिए, that is decided by this length of the tube. लंबा है, if the length of the tubes is long, then your diameter will reduce, or else if you are compromising with the length, then diameter has to increase to accommodate the given area for the heat exchange. So Tube dimensions incorporate the diameter, thickness and the length. Then next is select the pitch arrangement. Pitch is the center to center distance between the two tubes. Now this is a one tube and this is the another tube. So center to center distance is the pitch. So that should be equal to 1.25 times the outside diameter or 1.5 times the outside diameter. Outside diameter DO, that will incorporate the radius of the one tube plus the radius of the other tube, radius of the one tube plus the radius of the other tube. This is the DO. And 1.25 times the DO is this spacing. The next is in what arrangement these tubes they are to be arranged, whether it's a triangular pitch, square pitch or a rotated square pitch arrangement. Now if it's a triangular pitch arrangement, now I have drawn this with a triangular pitch arrangement. You can also draw with a square pitch arrangement. Then there can be a rotated square pitch arrangement also. So this is how the tubes they are arranged on the tube sheet. This is the overall tube sheet. इस ट्यूब शीट पे ट्यूब्स कैसे अरेंज है, that is of concern. That decides the amount of the pressure drop, that decides the turbulence created, and that decides the overall heat transfer coefficient also. So this pitch arrangement is having its own importance. The next is decide the flow of a cold fluid or the hot fluid placement in the inner tube or on the shell side. So hot fluid should be passed through the tubes or should be passed through the shell side. That is to be decided, that we will discuss in the selection of a fluid. The next is decide the number of passes on the tube side and on the shell side. For that purpose, we are having the pass partition plate on the tube side. Now if it's a heat exchanger that is there, and I am putting a partition plate here. There are a number of tubes which are available. So my fluid will come from this, will enter through these two tubes, will pass through these tubes, will change its direction and will go out from this tube. So this is my pass partition plate. The provided plate or separating the head. Now if you will look the transverse section for the head, there is a plate which is provided, and this plate provides first pass and the second pass. There are different arrangements that can be done for this purpose. This is the first, second and third, and this will go out from the third. So the different arrangements for the past partition flow, this is for the tube side arrangement. Similarly, in the exchanger, there can be the arrangements for the shell side also. That is the transverse baffles they are used. So on this side, the fluid that is coming in, the fluid will move like this and will change its path like this. So this is the movement of the fluid, or these are the longitudinal baffles. Then there are vertical or the transverse baffles. They are also available in the shell side. That is the intermittent flow which will be passing through that. So the fluid will come from this side, will move like this, will change its direction here and will go out from here. So depending on this number of baffles as well as the longitudinal transfer baffles, the number of passes that will be decided. The next is to calculate the outside surface area for one tube. Outside surface area for the one tube that is to be calculated. So if this is my tube, its outside surface area that is to be calculated. That means I am calculating using the DO as the outside diameter, the length of a tube, that is the pi DO into the L, that will give the surface area of one tube which is outside. Here we are doing the calculations for the outside area. Then the number of tubes that is to be decided. N is the number of tubes that can be used in the shell and tube heat exchanger. A is the total surface area which we have already calculated from Q, which is equals to the U A delta T. From this formula, we have calculated the area, and this area is the total area. So we are using this area, that is the total surface area required for the heat transfer, upon this surface area of the one tube. That will give me the total number of the tubes. Total area जितना है वो divided by the individual tube का area, that will give me the number of tubes. The next is the calculation of the bundle diameter. Depending on the how many number of the tubes, depending on the number of the tubes, so many number of the tubes that will be there. So all these tubes and the pitch arrangement, that is going to decide my bundle diameter. So bundle diameter dB, that will be equal to the outside diameter of the tube upon the into the n number of tubes upon k raised to the 1 upon n. It is raised to 1 upon n, where this n and k, they are the constants depending on the pitch arrangement, whether it's a triangular pitch arrangement or whether it's a square pitch arrangement. Based on that, we are having the bundle diameter that will be decided. Once the bundle diameter that is decided, you will be able to calculate the shell diameter, bundle diameter. That means the inside the tube, inside the shell and tube heat exchanger, there is a tube sheet that is available, and on that tube sheet there are the number of tubes which are arranged on the regular basis. this tube sheet diameter should be less than the bundle diameter. Then we calculate the diameter of the shell, which is equal to the 1.1 times the bundle diameter. The next is calculate the baffle spacing, that is the distance between the two baffles, longitudinal baffles. There are in the shell side, there are different baffles which are alternately arranged, and the flow will pass accordingly. From here the fluid will enter, it will move like this, it will change its path like this, again it moves like this, it moves like this, and it will go out from here. So this is the baffle spacing, that is the center to center distance between the two baffles, and which is equal to the ds upon 5 to the ds, and optimum values are 0.3 to 0.5 times the diameter of the shell. The next is the calculation of the individual heat transfer coefficient HI. So first, to calculate the cross-sectional area of one tube. Now, in this case, you have to calculate, you will be requiring the Prandtl number, Reynolds number, and the velocity calculations. They are of more concern. All this capital T, that is related to the tubes, and capital S, that is related to the shell. You have to remember this. Ut is the velocity of the tube, and Us is the velocity in the shell side. So this capital T and capital S, they are for the tube side, and that is for the shell side. So the calculations of the velocity is very critical in case of a heat exchanger designing, and which is having its own importance, that is the calculation of a velocity. So how to calculate the velocity, that we will first see. The total cross-sectional area of one tube is to be calculated. Why? There are n number of tubes, and for these n number of tubes, the total mass flow rate, that is the m, this much mass flow rate is passing through all these n number of tubes. So what will be the velocity to the individual tube? That is of my concern. And for that purpose, I have to calculate the cross-sectional area of the individual tube, which is AC, which is pi by 4 into di square. I am taking di here because the fluid which is passing through the tube, जो ट्यूब में से पास हो रहा है, उसके लिए मेरे को di लेने का है. ट्यूब के बाहर है तो आई विल कंसिडर द एरिया DO. ट्यूब के अंदर है तो आई एम कंसिडरिंग द एरिया कैलकुलेशंस बाय यूजिंग द इनसाइड डायमीटर ऑफ द ट्यूब. So the cross sectional area of the one tube, inside cross sectional area, this is, so pi by 4 into di square. Then number of tubes per pass, NP, that is to be calculated. So N is already the number of tubes upon the tube side passes. If there are two passes on the tube side. So the total tubes that will be divided into the tubes. If there are 6 tubes, say for example, so these 6 tubes are divided into the group of 3 tubes on one pass and 3 tubes on the another pass. So the fluid will enter through these 3 tubes only. Fluid will enter through these 3 tubes only, and it will change its path and again will move from these 3 tubes to go out. So this flow is divided by this pass partition plate. So I have to consider the number of tubes in each pass. That is the tubes per pass, which is equal to the number of tubes upon the tube side passes. Then the total cross-sectional area in one pass on the tube side, that is to be calculated. This is the NP, number of tubes per pass, into the individual cross-section. That will give me the total cross-sectional area in one pass. So इस one pass में total cross-sectional area कितना है? That is what this total mass flow rate is divided or is passing through the 3 number of tubes. That is why I have to calculate the cross-sectional area for these 3 tubes only. Then the velocity of the fluid through the tube, that is to be calculated. The mass flow rate for the tube, cross-sectional area in one pass, into the density of the fluid which is passing through the tubes, that is rho T. Rho T is the density of the fluid passing through the tube. Mass MT is the mass flow rate of the fluid passing through the tube. ACP is the cross-sectional area in one pass on the tube side. Once this calculation of velocity, mostly the students do calculation or mistake here itself. The calculation of velocity becomes wrong. As a result, our further calculations, they get spoiled. The next is the Reynolds number calculation. Reynolds number formula is our du rho by mu, the same formula that will be used. And this Reynolds number is du rho by mu. Now which d that is to be considered is the inside diameter, then velocity of the tube passing through the tube, velocity of the fluid passing through the tube, density of the fluid passing through the tube, viscosity of the fluid passing through the tube. That will give me the Reynolds number of the tube side. Similarly, the Prandtl number for the tube side fluid, that will be calculated by using the Cp mu upon K, that is Cp for the fluid which is passing through the tube, viscosity of the fluid passing through the tube, and the thermal conductivity of the fluid passing through the tube. Here you have to remember that the calculation of a tube side, you are going to use all the notations defined for the tube side. Viscosity for the tube, density for the tube, thermal conductivity of the tube, and the Cp of the fluid which is passing through the tube. This is most important. And then the calculation of the individual coefficient on the tube side by using the suitable relationship, that is, for example, Sider-Tatek correlation, Richter-Corbel relationship, or you can use the another relationships also. In case of a condensation, you can use the different relationship. In case of a boiling processes, you can use the different relationship to calculate the individual heat transfer coefficient. Now this Cedar Tata equation is 0.023 into RE raised to 0.8 into PR raised to N into mu B upon mu W, where N, that is 0.33 for if the fluid is cooling and 0.4 if the fluid is getting heated. So this is the RE through the tubes, Prandtl number through the tubes, that is to be remembered. And here HI is the inside heat transfer coefficient passing through the inside diameter of the tube DI and the thermal conductivity of the fluid passing through the tube. So this is going to give me the HI calculation. The next is the HO calculations. The shell side heat transfer coefficient. The area of a bundle cross section flow, that is to be calculated. Now, in case of a shell side velocity calculations, that is more complicated because the fluid that will be passing in between the two tubes. So this is my tubes which are arranged, and the fluid that will move in between these tubes. So I have to calculate the area of a bundle cross section that is to be calculated. That is AS, which is equal to PT minus PDO into the DS into the LB upon the PT. That is, PT is the pitch, which is nothing but 1.25 or 1.5 times the outside diameter of the tube. AS is PT minus DO. It should be PT minus DO only. This P is not needed. So this is DS, diameter of the shell side, LB is the baffle spacing, and PT is the pitch. Then the velocity of the fluid passing on the shell side, that is to be calculated. So in between these two tubes, what will be the velocity of the fluid? That should be calculated, and for that purpose we have calculated the available area. So velocity of the fluid passing on the shell side, which is equal to the US, which is mass flow rate of the fluid which is passing through the shell, into the area of the cross section, AS, and the rho S, that is the density for the fluid which is passing to the shell side. Then in calculation of Reynolds number, you require a diameter. So this diameter is nothing but an equivalent diameter that is to be calculated. Because the total shell diameter or the bundle diameter that is there, but the tubes are also available inside this. So what will be the effective diameter that will be used for the calculation of the effective or the equivalent diameter for that purpose? So that is 4 into cross-sectional area of the flow upon the weighted perimeter. And for that, you will be having the two different correlations for a triangular pitch arrangement and for a square pitch arrangement. You will be able to calculate the equivalent diameter DE. Then the Reynolds number calculation for the shell side, which is equal to the equivalent diameter capital DE and the velocity of the fluid passing through the shell side, density of the fluid passing through the shell, and viscosity of the fluid passing through the shell side. Then next is the Prandtl number calculation, that is Cp mu upon K, which is all related to the shell side. Then you have to calculate the individual coefficient on the shell side. That is HODE upon K, HD upon K, Nusselt's number, into the Reynolds number, into the Prandtl number, upon into the mu B and upon mu W. So there is a certain difference in the constants for the shell side calculation of the heat transfer coefficient. Here dE, that is to be taken as the equivalent diameter. Then mu B and mu W, that is mu B is the bulk viscosity of the fluid at the bulk temperature and viscosity of the fluid at the wall temperature. Whenever there is a tube and this tube will have the two temperatures. The surface which is near to this metal will have a different temperature, and for the bulk it will have a different temperature, and that is why we are using the mu B and the mu W. Mu B is the bulk fluid viscosity and mu W is at the wall. Then you have to calculate the overall coefficient, that is 1 upon U, which is equal to the dO upon di into 1 upon HI, plus this is the inside heat transfer coefficient, the outside heat transfer coefficient, and because of the thermal resistance, because of the metal wall resistance, and Ri and Ro are the fouling resistances, fouling factors for the inside and fouling factor for the outside. That is nothing but 1 upon HIB. And as we have already defined that this U is based on the outside area, and that is why it will be considered as the UO, that is the overall heat transfer coefficient based on the outside area UO, and that is why we have multiplied here by the dO upon di. You can also calculate the overall heat transfer coefficient based on the inside area also. So accordingly, the formula that will change. The next is calculate the pressure drop on the tube side and the pressure drop on the shell side. So tube side pressure drop, that is should be calculated